Alright, good evening. Welcome to lecture 1.6 of Unit 2, Binding Energy. Here are the learning intention and success criteria for this lesson. Please pause the video and attempt to complete the KS table over on the right there. Alright, so having a look through here, there's a few new terminology. We've got this one, mass defect and binding energy. One of the requirements is that we're able to define this. Binding energy is something we can calculate, so there's our next success criteria. We need to calculate the binding energy. And finally, we need to be able to represent this energy value both in joules, which we're kind of used to, and electron volt. So there's a new unit that's going to appear here. So for our KS table, what does mass defect mean? What does binding energy mean? What's an electron volt? In terms of skills, well, can I calculate binding energy? So, if you look at the mass of an atom, and I mean the actual specific isotope, not the average mass on your periodic tables, and you work out the mass of all the individual protons and neutrons, you'll find they don't actually match. Some of the mass is missing. So here is an example of uranium-238. Uranium-238, here is the mass value. You can find that on internet searches. Wikipedia is actually pretty decent for getting isotope masses because it's just data. The mass of uranium has 92 protons. 92 times the atomic mass of one proton gives us that number there. It has 146 neutrons. Multiply 146 by the mass of a neutron, we get that number there. And then finally the mass of the electrons. While normally we wouldn't bother with the mass of the electrons, I wanted to include it in this time just so that you can see, well, even with 92 electrons, it's only adding it's adding 5% of one atomic mass unit. So really, when you're dealing with the electrons, don't matter too much, and we're not even going to worry about that precision really. So if we look at the total mass there of adding those three bits up, though, we have 239.98 compared to an actual isotope mass of 238.05. There is some mass missing. Now, this is called the mass defect, and it represents the binding energy of an atom. So the mass defect is the missing mass between, if you add up all the pieces, versus the actual mass of the isotope. Now, the reason it represents the binding energy of an atom, and we'll talk about what that actually means in a second, is because Einstein connected mass and energy together through his work on special relativity, which we'll be looking at later on, and developed this equation that you've probably seen. E equals mc squared. Now this is just a small part of the equation. The full equation is a little bit longer and also deals with things that are moving at the same time, but we just need this bit for our topic. Now c is a constant here and stands for the speed of light, which is 3 times 10 to the 8 meters per second. So if you take a very small difference in mass and you chuck it in this equation, you will get the binding energy of an atom, and that creates the stability of an atom. Okay? And what we mean by that is that if you have more energy holding the atom together, it's more stable, and we can work out, well, how much of this missing energy, this binding energy, is there per the number of nucleons, the number of protons and neutrons in an atom, and that gives us the stability. In fact, if we graph this out, we see a very interesting shape. So we can see here on the left, everything starts off quite low, slowly builds up, gets to a point here, and then arcs down to the side. So uranium-238 is all the way down here. This bit in the middle, these are the very, very stable. They don't generally go through decay. But as you go down here, you're more and more likely to get decay. As you go here, you're definitely going to get some instability. You can see there's two regions here, fusion and fission. Now we'll look at fission in the next video, and fusion will be in a couple of videos. So we'll come back to this graph over the next couple of videos. For now, we just need to understand, well, binding energy per nucleon, if I take the energy and I divide it by the mass number, the number of protons plus the number of neutrons, I'm going to work out some function of its stability. So let's have a look at the example from before. So here is our data for uranium-238. We've got our mass here in atomic mass units. The thing is, we need to turn that into kilograms, because E equals mc squared does take just the normal default units. It produces an energy in joules, it needs a mass in kilograms. It's going to be a small number, but you will see that it still produces a fair amount of energy. So, total mass here is 239.98 atomic mass units. Oops, where's my... 230... well, firstly we need to know the mass defect, 239.98, take away 238.05, which will give us 1.93 atomic mass units, and that's going to be our mass defect. Now I need to turn that into kilograms, multiply, and the conversion is 1.66 with a couple of extra numbers after it, but I'll just do it to 2 decimal places, times 10 to the negative 27, and then that will give us the mass in kilograms. Calculator. Now remember this conversion, the how many AMU to kilograms, that is provided in your formula sheet, so you won't need to worry about memorizing that number. Times 10 to the negative 27, and we get a value of the mass 3.2 times 10 to the negative 27 kilograms. I mean, that's a pretty small number, and we're not even going to hit to 1 joule, but remember, this is about one singular atom, and one singular atom, I mean, is not weighing very much. We're normally dealing with chunks of uranium in the grams, which means that you've got a lot of atoms, and all these atoms release this energy. This is where we get our gamma energy calculations from. So let's look at our energy value now. E equals 3.2 times 10 to the negative 27 times 3 times 10 to the 8, and that is squared. Now, do be careful putting this in a calculator. I've had students do this times this, and then they'd square the whole answer. That's not correct. You have to do this times this thing squared. So if you need to, and your calculator skills are a bit choppy, do this first. Do 3 times 10 to the 8 squared, or you can just jump straight to 9 times 10 to the 16. If you're uncertain of how to do that, either you're watching this and you're in grade 9, or you're watching this and you can't remember your index laws from last year, in which case go to Khan Academy and get checked. 3.2, 10 to the negative 27, multiplied by 9 times 10 to the power of 16, and we get an answer of 2.88 times 10 to the negative 10 joules, and that's our binding energy. It's as straightforward as that. Now this might not seem like much, but again remember, this means this is from one singular atom. If we had a mole worth of atoms, so Avogadro's numbers worth, which is 10 to the 23rd power, then we'd have 10 to the power of 13 joules, probably 10 to the 14 joules worth of energy being released from 1 mole of uranium, if we were to break it apart into its constituent pieces. So this is how we work out mass defect. Look at the mass of the bits compared to the mass of the actual atom, and then this is how we convert it to some binding energy. Okay. Now, this number is pretty small, and mostly we don't like writing things with very small powers all the time. And so we have another type of unit for representing energy, okay? And this is called the electron volt. And this is often how we will express information about the energy contained within an atom. Now the conversion is very straightforward. It is in your formula booklet. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. This number is because that is the charge on an electron. We'll see that when we do electrostatics and electromagnetism next year. The conversion is in the booklet. You don't need to memorize it, so if you forget it, just go check your data booklet. And it is just a unit conversion, so I'm not really expecting you to need to worry too much. One thing of note that I always use as a check, if I have a small energy, my electron volt should be a whole number. So we'll do one. Actually, I will do one conversion. I wasn't going to, but we'll do one anyway. So let's go back. This was 2.88 10 to the negative 10. So 2.88 times 10 to the negative 10 joules. Now the conversion is this many joules gives us 1 electron volt. So if I divide this number by this, I will get the number of electron volts I have. One way to sort of help you remember how to do this is that I can set up proportion equations. So if I go 1 electron volt is 1.6 times 10 to the negative 19, and I need to know some new value of electron volts. That's going to be equal to 2.8 times 10 to the negative 10. Well, this divided by this will equal this divided by this. X divided by 1 is just x, but we can see here now if I divide these two numbers, I'll know what my missing value is. 2.88 into the negative 10 divided by 1.6. Be careful with this, make sure that it actually is dividing by the power. You'll know if you've done it right, because if I do 10 to the negative 10 divided by 10 to the negative 19, it'll give me a positive 9. If I do 10 to the negative 10 divided by this, and then multiplied by 10 to the negative 19, I'll get around 10 to the negative 29. Right? So that is a way to check. Now the answer to this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 1.8 times 10. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 electron volts. Often we will put this into some value of electron volts. So for example, this would be 1.8 times 10 to the 3 mega electron volts, if we were to put it like this as well. So you may have combinations of scientific notation and what's the word I'm looking for? Metric system prefixes, and while these are provided in your notebook, you sort of need to know how to read them. Okay. There is some really good discussion about typical number of electron volts when you deal with atomic masses in the text. Definitely have a look at that, and that's in chapter 4.2. The key thing is that you need to take away from it, though, is that sometimes, sorry, I've written over the top of that, sometimes atomic energy will be presented in electron volts, and you just have to go, oh yeah, that's an energy, I've got to convert it. But because those four formulas do require you to work in joules, you must do your conversion. Okay, fairly straightforward. Have a bit of a play with it, you'll get the hang of it. So, this video, quick one, but we've gone through the following couple of things. We have examined the binding energy of an atom as it relates to mass, and we've introduced the topic of the electron volt. In terms of your entrance slip, please have access of chapter 4.2, check your learning, and look at questions 1 to 5 in chapter 4.2. These answers will go into the 2.1.6 space on eLearn. Thanks very much for listening, guys. Have a great evening.